Hello everyone, my name is Yusuf Aitaddo. My matric number is 195460, and I will start with the introduction. So Laplace equation is a very important equation in the scientific domains, especially in physics, and it is also known as the potential equation. That is because every physical field that satisfies the Laplace equation or the potential equation is called a potential field. For example, gravitational, velocity, electric and magnetic fields are all examples of potential fields. This equation here has a solution and is called the harmonic functions. These functions here are used to path plan the potential fields related to the Laplace equation. In this project we will use two applications of these functions. The first one to use harmonic functions in the steady state of the equation, and the second one to use it in the potential fields of obstacles based on hydrodynamics. We will use the definition of Laplace's equation and the harmonic functions. A function f is called harmonic if it is of class C2 and satisfies the Laplace equation. The Laplacian of f equals to 0, which also means that the divergence of the gradient of f equals to 0.
Okay, I will start with the methodology and results. Firstly, the first application for the harmonic function is the steady state temperature, where there are two dimensions that is going to be explained. For one-dimensional space, to develop the heat equation that is not time dependent, we can construct a function that involves function u and x in one space variable, where function u is given ut is equal to k u xx, where ui is equal to 0 for all x and t. Meanwhile, function of x alone need to satisfy uxx is equal to 0. If we let u equals to ax plus b, where a and b are constants, and suppose we have an isolated wire, we apply the constant temperature T1 at one end, where x is equal to 0, and another temperature T2 at the other end of the rod, where x is equal to L, which is the length of rod. Then we obtain the steady state solution of ux is equal to T2 minus T1 over L times x plus T1.
For two-dimensional space, we have the heat equation which involves both the x and y. So the heat equation becomes ut is equals to k uxx plus uyy, where this uxx plus uyy can be written as delta u. And the solution for this equation could be obtained, which is actually the harmonic function uxy that doesn't depend on time. And this is an heat equation, so there is surely a boundary value problem known as the Dirichlet problem. And for this, we should have a region, and here we take a rectangular region as an example. So the Dirichlet problem is as follows, where delta u is equals to 0, u when x equals to 0 is equals to 0, where y is greater than 0 but less than h, and when when y equals to h is equals to 0 for x greater than 0 but less than w, when x equals to w, u becomes 0 for y greater than 0 but less than h, and at y equals to 0, u becomes fx for x greater than 0 but less than w. So in order to find a solution, we let our uxy to be capital X, x, capital Y, y. And here we have to differentiate this equation twice, as we know that the harmonic function should satisfy the Laplace equation. So by differentiating it, we get as capital X double prime X y y plus x x y double prime y is equals to 0. By using the separation of variables technique, we can get as negative x double prime x divided by x x is equals to y double prime y divided by y y, and these two we let them equals to lambda, where lambda is a constant. By this step, we get two equations, which is x double prime x plus lambda x equals to 0 and y double prime y minus lambda y is equals to 0. Now for both this equation, we only get non-trivial solution if lambda is equals to lambda n is equals to n square pi square divided by w square. This one we get from the boundary value problem such that x0 is equals to xw is equals to 0. Next, after getting this value, we can get for yn, where y is equals to an cos n pi over wy plus bn sin n pi over wx. We know from the boundary condition also that yn0 is equals to 1. So we can let an to be 1, and by taking y and h is equals to 0 from boundary condition also, we get bn as negative cos n pi h divided by y divided by sin n pi h over w. And some simplification will give us y and y is equals to sin n pi h minus y divided by w divided by sin n pi h over w. Now we have that u and xy is equals to capital X and x, capital Y and y. So by taking y equals to 0 and y equals to 0, we get that x and x, y and 0. And here we know that when y is equals to 0 from the boundary condition, we only left with fx, which is actually the sin nh over n divided by x. Sin n pi divided by nx. Suppose that we have fx such that a summation from n equals to 1 until infinity bn sin n pi x divided by w, then we have uxy as follows. Okay, let's see an example. Suppose that we have w is equals to h equals to pi and fx equals to pi. We compute the sine series for the function pi. We find that for x greater than 0 but less than pi, we obtain fx equals to summation from n equals to 1 until infinity 4 divided by n sin nx. The solution uxy to the corresponding problem is given as uxy is equals to summation n equals to 1 until infinity 4 divided by n sin nx sin n pi minus y divided by sin n pi. This is for actually for all n values, and from here we can find the coefficients like a3, b3 and also bn, and these coefficients are also for n equals to odd and n not equals to 3.
Second application, we have the real-time obstacle avoidance. Potential fields for obstacle avoidance built by harmonic potential function, and this is the equation that is used to derive the repulsive force of obstacles and the attractive force of a goal position by using its source or singularities. Meanwhile, to derive a more effective artificial potential field from a starting position to a goal position, we use this equation. And next, harmonic functions able to eliminate the local minima. The artificial potential hold as follows. This is the harmonic functions, and this is the non-harmonic functions. The panel method was introduced for modeling obstacles. For single panel, they showed the oncoming stream can be deflected by single panel of distributed sources. The expressions for velocity components is given by this. And the potential and velocity components of the uniform flows followed as these three. Thus, the obstacle avoidance can be presented as Vn equals to negative u or 0 y more than 0. There are some observations such the location of the stagnation points, the fluid particle and unbounded cases can be made from the comparison of the figures. For multi-panels, they used these following velocity equations to derive a trajectory for real-time control. The closed form potential function is given by the panel method and can be easily applied. During real-time control, the shape of a robot can be easily considered as its computation time increases linearly. For non-point robots, a control strategy under potential field is developed by panel method and harmonic function. It is tested with mobile robots and redundant manipulators.
So now I will continue to explain the example of 9-point robot, which is mobile robot. The shape of the mobile robot is kind of like this. You can see the bar shape mobile robots, and the displacement of the primary control of the angle of the angle per period is obtained during the potential operation, which are delta x equal to u xy and delta y equal to v xy, and the delta eta equals to tan inverse vxy over uxy, which is we can also set its delta n equals to tangent -1 delta y over delta x minus n. Here, a bar-shaped mobile robots also have 3 degrees, which is 3-degree freedom, which is x, y, and n. So that we can see from the equation, you can see 3 x, y, and n. We can see that. Okay, so the fluid particle that goes to an obstacle has a longer trajectory to travel in the same time than particle from an obstacle. So the displacement are adjusted by the directional information and the maximum possible displacement per period by, this is the equation for delta x, which is we have the maximum displacement cos bracket n bracket eta plus delta eta bracket, and we also have a y equals to displacement maximum sine eta plus delta eta. Okay, so when the assumptions of the angle change to have a maximum saturation per period, they have made some adjustment to the equation. So, which is we can conclude that delta eta is larger than delta eta maximum, which we have h equals to delta eta maximum over delta eta, and we have, when we substitute to the equation, we have delta x equals to delta x times h. We also have delta y ay times h, and delta n equals to delta eta times h. And for example, yeah, so here we have as given value follows m equal, this is m marked as panel, which is we can see in the table panel 1 until 16. So u 1.0 alpha g equals to 30, v I equals to 0.5, and I here equals to 1, 2 until 16, which is the value of the m. The given normal velocity at the center points of each panel is satisfied as the panels able to overcome the problem occurred for the concave obstacle here. The goal has been achieved by the bar-shaped mobile robot as the table below shown. It is the result is as expected as the harmonic function's potential is applied. So here we can see when the panel 1 is equal, when the panel is 1, the strength is equal to negative 4.955, and the research continue until the panel, the M equal to 16. So we can see that when M equals to 16, it is equal to, the strength equals to negative 1.364. Okay, this is the panel, this is the table for panel and the strength of the mobile robots. That are the examples of harmonic functions. That's all from me. Thank you.
In conclusion, we have seen that harmonic functions have an important role in solving many real-world problems. In this paper, we have seen two different applications of the harmonic functions. The first one is a classical approach to solve Laplace equation related to the steady state of heat equation. Next, we have discussed how we can use the harmonic functions in solving motion planning of robots based on potential fields of obstacle avoidance. And these are our references. Thank you for your attention.